Goodness of fit's a little different than the other procedures we've had, and so I'm gonna get to it by backing into it. I'm gonna start off slowly and build it up. And when we're all done, then we'll know what it is. But bear with me for a while, okay? First of all, it's a non-parametric test. That means it doesn't require that the data we work with be normal. The data may very well not be normal data. So we're working with general data. In goodness of fit, there are things we call categories. Example of categories, let's say the color of hair, blonde, brunette, blackhead, redhead, and other. I have 1, 2, 3, 4, 5 categories. These would be called levels of a factor in other branches of statistics. But in goodness of fit, they're called categories. So levels of a factor are now the categories, and there are 5 of them. The counts, or what we call the observed values, are the observed number of each of these. How many blondes, brunettes, redheads, and blackheads and others did we observe? How many are in each of these categories? How many? There are 5 observed values. There are 5 counts. Now, that's a little tricky. Let's take an example. Out of 100 people surveyed, I go to the drill field and I check the first 100 people that pass by me, and I find that there are 31 blondes, 54 brunettes, 10 blackheads, 4 redheads, and 1 other. Well, someone says, all right, how many observations do you have? And clearly I have 100 people, so I have 100 observations. Well, that's in all the other branches of statistics. We mention all of the procedures. We would agree, yes, there's 100 observations. And maybe there are 100 observations. But the observed values for the goodness of fit procedure are 1, 2, 3, 4, and 5. There are 5 numbers. This is one of them, 2nd, 3rd, 4th, and 5th. There are 5 observed values, 5, not 100. The 100 don't count. That's what's used to find the 5 values. But we have only 5 different numbers. They're sort of bits of information. We start out with 5 bits of information. These are bits of information. What we used to call degrees of freedom, we will again. These are bits of information. However, not all the information is useful. There's a thing called a constraint. A constraint is a restriction on the counts which eliminates the need to know one count. If I don't need to know a count, then I have a constraint. The constraint is what causes me not to need to know that count. Well, let's have an example. Out of 100 people, 31 blondes, 54 brunettes, 10 blackheads, 4 redheads, and whoops, I lost the rest of my data. And someone comes along and says, aha, you lost the rest of your data? You want to buy it? $100. I'll sell you the missing number. And I look at him and I say, you got to be crazy. I know the missing number. I don't need to have it written on a piece of paper. There were 100 people surveyed. I have accounted for 99 people. Therefore, there's only one possible number that could fit there, and that's 1. So I don't need to know that number. The constraint, the fact that 100 people were surveyed, is a constraint because it allows me to do away with one of these numbers. I do not need to know it because this tells me what it is by subtraction. Well, if I have a constraint and I started out with 5 numbers and one of them is not needed, then I have only 4 bits of information, really. I have to really take care, subtract off a bit of information because I have a constraint. Like we used to subtract a bit of information because we had an estimate. Now we're subtracting a bit of information for a constraint. Same kind of situation. The degrees of freedom. The degrees of freedom. We said degrees of freedom were bits of information, remember? They are the number of independent bits of information. And usually it's the number of categories minus the number of constraints. The number of categories is how many numbers we have. And they represent a bit of information each, unless I have a constraint. If I have a constraint, I don't need to have one of those numbers. One of those numbers is not independent of the rest. I can find it without having it. Well, then I have to subtract from the number of observations, observed values, I have to subtract each of the constraints that I have. And if I happen to have any estimates, I will also subtract off the number of estimates. Right now, for this example, we don't have any estimates. But if I had, I would subtract it off. Okay, we keep going. We haven't gotten anywhere we can sink our teeth into yet. Just some notation. There's an assumption. There's an assumption being tested. That's what we're trying to test. What we're going to do, goodness of fit, is actually a test of a hypothesis. What is being tested? Well, some assumption. Something is being tested. We'll call that an assumption. The assumption, in order to be tested, must influence the counts. Well, why on earth are we doing this experiment if not to test the assumption? Well, if we're going to test the assumption, then the assumption better have something to do with those counts. Or it would be silly to do an experiment doing counting when it has nothing at all to do with the assumption. So the assumption had better have something to do with the accounts. In fact, the assumption is used to test the counts, or vice versa, actually. The counts are going to be used to test the assumption. What's really happening is someone makes an assumption, and that assumption determines what the count should be. And then we go look at the counts and we say, oh, that doesn't make much sense. The data that I have is inconsistent with your assumption, and I can reject the hypothesis. This is where we're heading. We have an assumption. The assumption influences the counts, but the counts don't seem to represent the assumption. Something's haywire here. If there's enough discrepancy, I say, oh, no, I don't believe that assumption at all. The actual data belie the assumption. This is where we're headed. Let's see how we get there. What happens is that the assumption being tested provides expected counts. Expected counts. How many there should be in each category. Then I look at how many there were in each category and I see if they're close. That's essentially what we're going to do. Okay, let's look at these expected counts. The expected counts are the expected counts for each category. When I talk about expected counts, I say, well, how many should there be in each category? How many blondes should there be? How many brunettes should there be? How many redheads should there be? How many blackheads should there be? How many others should there be? Okay? Note, expected need not be whole numbers. Counts have to be whole numbers. Like the dots on a die had to be whole numbers. When I rolled the die and looked for an expectation, I had 3.5. 3.5 is not a whole number. Expectations do not have to be whole numbers. Expected counts need not be whole numbers. And I think it's time for a numerical example. Let's take something which we'll get our teeth into. Let's take the example, roll one die 10 times. Okay, we're going to roll a die 10 times. The assumption that we're going to test is that each face is equally likely. That's a fair die. Fair die, each face is equally likely to come up. We roll it 10 times, and we're going to check this assumption. Well, what's the expectation? Now, I'm cheating here. I'm cheating. The expectation, I claim, is 10.6 or 1.67. And you're going to say, wait a minute. Everyone knows the expectation, if you roll a die, is 3.5. And if you roll it 10 times, then you should get 35. So, isn't that right? Yeah, that's right if you're looking for the expected number of dots facing up. But we're not the least bit interested in the dots facing up. What we're interested in is the expected counts. Okay? And we want to know how many ones should I expect? How many twos should I? If I roll the dice 12 times instead of 10, let's roll it 6 times. Make it easy on us. 6 times. Roll it 6 times. And I have faces 1, 2, 3, 4, 5, 6. How many of each should I expect? 1. If I rolled it 12 times, I should expect 2. If I rolled it 18, I should expect 3 of each. But I rolled it 10 times. So I expect 10/6 or 1.67 times per face. Let's spread our example out a little here. Category is the face of the die. I have 6 faces to my die. That's my categories. I go out and I roll this thing 10 times. And let's say, for argument's sake, I observed 1 1, 2 2s, 3 3s, no 4s, 2 5s, and 2 6s. How many should I have observed? Well, if they're equally likely, as the assumption says, and I roll it 10 times, then I should expect each one to come up the same number of times. And the number which does that is 1.67, 1 2/3 times each. Now, remember, expectations do not have to be whole numbers. And of course, you can never obtain 1.67 times. You can never get a 1, 1 3/4, 1 2/3 times. You can never get a 3, 1 2/3 times. However, this is the expected number. Here are the observed numbers. Now, clearly, the observed and the expected do not match. They never match. They can't possibly match. Are these observed far enough away from the expecteds for us to be able to say, something's fishy here? I don't believe the null hypothesis that they're equally likely is true, because if they were true, then the observed data would be closer to the expected data, and I wouldn't have gotten this large variation. Well, if it is a large variation. We have to be able to do that. In order to do that, we continue on. We're not there yet. We don't know how to do it yet. We're gonna try. The question we ask is, are the observed far enough from the predicted for us to reject the assumption? Now that means at the 10% level, or the 5% level, or the 1% level. Those are the levels we do our tests. And do we have enough information? Are we 90% sure? Are we 95% sure? Are we 99% sure that the assumption is wrong? Well, pretty difficult just to look at the numbers and tell. The null hypothesis is the assumption. We're that far. We have the assumption. We have the data. What we don't have is the test statistic. We need a test statistic in order to do this. So I'm going to give you the test statistic we used in goodness of fit. We're up to it now. It's the chi-square statistic. It's called the chi-square, or sometimes called the chi-squared statistic, depending on who you speak to. And what it is the following. This is chi, the Greek letter chi. Chi-squared statistic is the sum of. What you have to do is, for each of the categories, there's an observed value and there's an expected value. Take the difference between the observed and the expected value and square that quantity. Then divide that quantity by the expected value. Do that for each of the categories and sum them up. And that sum is called the chi-square statistic. Now, the chi-square statistic, if the observed, if things were perfect, the observed and the expected would be equal, and this would be 0. Even if they're not perfect, but they're close to perfect, this would be a small number, small. If the expected and the observed are far apart, this will be a large number. So, chi-square, is it large enough for us to reject? Is it large enough is really the question we're going to ask. Here's our example. In our example, we had these dice. Remember the dice? And this was the observed number, and here the expected number. In order to start getting the chi-square statistic, I take 1 minus 1.67, which is minus 0.67. I square it, and I divide by 1.67, and that comes out to be 0.26. I take 2 and subtract 1.67. That gives me about 0.33. Square that and divide by 1.67. That gives me 0.06. And I do that for each of these, and here's what I get. 106, 167, 26, 106. And I sum them up, and the sum of them is the chi-square statistic, and it's 4.37. And now the question is 4.37 big enough for us to be able to reject the hypothesis? Well, in order to do this, we have to have either a computer or a table. And I'm going to show you how to actually do a chi-square test, because in the next lecture you will be getting something that I really want you to do. In fact, you can actually do this one, because here's the table. Here's a short table of p-values. Remember, what we had for the chi-square value was 4.37. The degrees of freedom were what? We had, let's see, 6 categories, 1 constraint, 5 degrees of freedom. 5 degrees of freedom. All right? 4.37, 5 degrees of freedom. Maybe, all right? That puts us where on this table? And people say, oh, it's not on the table. Because here are the p-values. Here are the degrees of freedom. I'm at 5 degrees of freedom, so I'm in this line somewhere. I'm here somewhere. And now I have to find what p-value corresponds to 4.37. Then the answer is 4.37 is somewhere over here. What's the p-value corresponding to that? I don't know, but it's certainly bigger than 0.1. Pick a number, I don't care. Say 0.3, right? It's certainly something like that. Well, if I know p-value is 0.3, I'm finished, because I know at alpha equal 0.1, at alpha equal to 0.05, at alpha equal to 0.01, I must fail to reject. The reason for that is because I can only reject when the size or level of the test is larger in magnitude than the p-value. And nothing is larger here than a number to the left of it. The numbers to the left of it are all bigger. So I will always fail to reject. For this set of data, I must fail to reject. Well, this table can be used for most anything. We saw something off the table. If you had, let's say you had a chi-square value of 30, and you had 18 degrees of freedom. Okay? What would you do? Well, 18 degrees of freedom would put you somewhere over here, in here. 30, that means here I have, from 22 to 34. Oh, that's too close. Too close to call. Let's make it, well, maybe not. 22 to 34. This is sort of halfway between, so this is around 28. Here, around 20. Here's 28 to 37. This is around 34. So 30, if there was a 30 on this line, it would come out somewhere over here. And that would give me like a 0.08, say. Now, it doesn't matter if it's 0.09. I don't even care if it's 0.095 or 0.055. It's somewhere between here. That's all I have to know. Once I know it's between here, and someone says, make a 10% level test, I would say reject, because 10% is bigger than the p-value of 0.08. If someone said make a 5% level test, I would say fail to reject, because 5% is less than the p-value of 0.08. So for this situation here, the p-value is 0.08, or approximately. Any rate, it's somewhere between. It's between 0.1 and 0.05. It's somewhere in here, and I don't care where it is in there, as long as I know where it is. Okay? That's how we use this table, and we can solve any of the problems you like. Now, what I do in class, and I'd like you to try it at home if you will, just to get some experience with this, because you may very well be using it. Roll a die 10 times, record the counts, calculate the chi-square value under the assumption that the numbers are equally likely. That means 1.67. Approximate the p-value, and then reject or not reject, and see if you can do it with your data. Now, the reason I gave you the table and the arithmetic is because people are often asked, students are often asked to do statistical tests in classes. And invariably, the one that they use is the goodness of fit test. It's the most appropriate because it doesn't require the data to be normal. It doesn't require any particular kind of data. It is a very, very general procedure, a very general procedure. It's used in the courts. Lawyers understand it. Judges understand it. It's used very much, and in most cases, I always say statistical procedures are abused. Well, goodness of fit is not being abused, it's being used. It's only time you abuse it is when you confound things. You say, I'm testing one thing, when you're really testing something else. But the statistics itself, the actual doing of it, is rather straightforward, and you can't make much of a mistake. And I would advise you to learn it. And so if you ever do have to do a statistical procedure, you will have one under your belt. Okay? Good luck.